Okay, good morning. We are going to continue our study this morning with the study of the Laplace transform. And one of the advantages of the Laplace transform is that it enables us to work in the algebraic domain, given certain circuit problems that takes on some differential equation. The Laplace transform allows us to transform it from a differential equation into some algebraic manipulation, where it can be probably relatively handled more easily. So that's one of the advantage. It transforms responses and behaviors, scientific behaviors that is described via differential equation into algebraic equation and algebraic description. Alright, the Laplace transform was credited to Pierre Simon Laplace. And he was 1749 through to 1827. French astronomer and mathematician. We're not going to spend much time on the chronology and the history of this mathematician and astronomer, but we're just going to jump straight into the definition of the Laplace transform and how it is used and when it is used. What we wish to help us to solve certain circuit problems, certain natural response or force responses. Later on we'll come on to the Fourier transform, which is sort of a similar sort of a transform, transforming from the one domain, frequency domain, into a time domain, and vice versa. Time domain into a frequency domain, and from frequency to time, via the transform and the inverse transform. So you have the Laplace transform and the inverse Laplace transform. Alright, so let's get into it by the definition. My name is Dolphy, and we say that the definition of the Laplace transform. So this is the symbol, the Laplace transform of f of t, some function f of t is equal to, say, f of s is equal to the integral from 0 to infinity of f of t e to the minus st dt. Yeah, that's our definition of the Laplace transform. Furthermore, we say now that this S is equal now to sigma plus j omega. The real portion, sigma, and the complex portion, j omega. Alright, we could see now that this Laplace transform, this is called the unilateral Laplace, or one-sided Laplace transform. That the bilateral, two-sided Laplace transform is that now we say that's the f of s, which is the Laplace transform, is equal now to the interval from minus infinity to infinity of f of t e to the minus st. bilateral or two-sided Laplace transform. And this is called unilateral or one-sided Laplace transform. And we'll be dealing mostly with the unilateral or one-sided Laplace transform. So let's straight into doing some problems. So once again, we say that the transform itself helps us to transform certain Laplace transform is an integral transformation of function f of t from the time domain into the frequency domain. So that is like the definition of the Laplace transform is that it's an integral transformation of a function f of t from the time domain into a complex frequency domain. And so we gave you before the unilateral f of t equals to f of s equal 0 to infinity f of t e to the minus st dt. Bilateral once more, Laplace transform f of t minus infinity to infinity f of t e to minus st dt. Bilateral. Two-sided. Alright, with that, let us move into solving some problems. So we take first, let's say, the unit step. Some function u of t as a unit step. Graph of a unit step would be like so. We wish to find the Laplace transform of the unit step. So what we do, we say the Laplace transform of u of t is equal now to the integral 0 to infinity of 1 times e to the minus st dt. Yeah? Unit step. It's one all along this line. And 0 everywhere along the t-axis. And 1 everywhere along the u of t axis, which is why it's called a unit step. And so if we take if we work out this, we'll get now the integral of some exponential function. You get by the exponential function and divided by the minus s. So that will be e to the minus st over s. 0 to infinity. And that's equal now to, if we take us this tend to infinity, e to the minus st will tend to 0. And s over 0 will be 0. So that will be 0 for the first part. And that will be minus now minus e to the minus st e to the minus 0 is 1 over s. That's equal now to 1 over s. Minus is plus, so that's equal to 1 over s. Yeah, so that's the Laplace transform of the unit step. Let's go on to another. Let's go on to an exponential function of, say, Laplace transform of e to the minus at dt. And we draw a curve for that, something like so. So this is the exponential. And so we say now the Laplace transform of e of at is equal now to the integral from 0 to infinity by the definition. E to the minus at, e to the minus st dt. You must remember that s equals sigma plus j omega. And so that's equal to integral from 0 to infinity e to the minus into a plus s t dt. You add the exponent and I factor out the t. After adding the exponent, because that's the rule for multiplying two exponential functions, e to the minus a plus s t. And so if we integrate that now, we get back the same function, which is e to the minus a plus s t, and divided by minus a plus s. And this is taken now from 0 to infinity. Okay? Let me see the one the constant is going to disappear. So let's take it out. So we have that's equal to this function now as it tends to infinity, it tends to 0, and that upon 0 will be 0. And e to the minus 0 is 1. Anything to the 0 is 1. So we have no minus 1 upon minus into a plus s. And that's equal to 1 over a plus s. S is equal to sigma plus j. So the answer to the exponential function, the Laplace transform, as we transform it from time domain into a complex frequency domain, or from a differential equation format into a algebraic format. So the end of the transform is that it turns out into an algebraic sort of a format. So we have 1 over s for the unit step, and we have 1 over a plus s for the exponential function e to the minus at. Let's take a short break and